The next contributed talk is from Jonas Mielke, also from Konstanz. The title is Nuclear Spin Readout in a Cavity-Coupled Hybrid Quantum Dot Donor System. Jonas, I think you are all set, so please go ahead.
Okay, sure. So you see my slides, right?
Yes, it works.
Okay, perfect. So yeah, as you already mentioned, I'm talking about nuclear spin readout. And the motivation to consider nuclear spins in general is, of course, that their good isolation from the environment leads to long T1 and T2 times and makes them promising candidates for quantum information applications. But before discussing the readout technique, I'd like to point out a previous finding that is fundamental for our readout method. So if you have a single electron in a double quantum dot, the system can be seen as a charged qubit with a substantial electric dipole moment, such that the charge of the electron can couple to a microwave resonator, while the electron spin does not. However, if you introduce a magnetic field gradient, the spin and the charge of the electron hybridize, and this leads to an indirect electron spin-photon coupling. And this coupling can be tuned to the strong coupling regime. And if you do so, you get this signature in the cavity transmission that is shown in the plot here that gives the transmission as a function of the external magnetic field Bz, that determines the Zeeman splitting and the double quantum dot energy level detuning epsilon. If you now add a longitudinal magnetic field gradient, both the the amplitude of a response of the transmission shift, and this observation motivated us to check if there's a similar nuclear spin state and dependent effect. So the specific system we are considering is basically a silicon quantum dot donor architecture with a single electron, and this system couples to a microwave cavity. To be a bit more precise, the quantum dot and the donor energy level are detuned by an amount epsilon, and they are hybridized by a tunnel coupling strength Tc, while the electron, while the spin of the electron is subject to a homogeneous magnetic field Bz and the thereto perpendicular magnetic field gradient Bx. The charge of the electron couples to a microwave resonator or to a single mode of a microwave resonator with frequency omega c, and with electric dipole coupling with dipole coupling strength Gc as given in the Hamiltonian here. Then we can imagine two extreme scenarios. So in the one case, the electron is bound to the donor, and then electron spin and donor nuclear spin interact via the hyperfine interaction. On the other hand, if the electron is completely confined to the quantum dot, there's no hyperfine interaction between the electron spin and the nuclear spin. So everything I've discussed now is covered by this Hamiltonian here, where the operators tau are the position space Pauli operators, sigma are the electron spin operators, and nu the nuclear spin operators. So during this talk, I'll try to convince you that the cavity transmission that is given by the ratio of outgoing field at cavity port 2 and incoming field at port 1 reveals information about the nuclear spin state. So let us first have a look at the energy spectrum of the quantum dot donor system, neglecting the cavity at first. So if you only have these two first terms, you get these crossing energy levels that correspond to the electron either being located at the quantum dot or at the donor on the right. Switching on the tunnel coupling hybridizes these L and R states with identical electron spin, and you get these energy levels shown in black, and the associated eigenstates labeled by plus and minus resemble bonding and anti-bonding molecular orbital states. And the composition of these states is determined by the orbital angle theta. In the end, we can also look at the effect of the magnetic field gradient and the hyperfine interaction. And if you include these terms, you get these red energy levels. And I have to mention that for this plot, exaggerated values for A and Bx were chosen, just to emphasize the effects. But nevertheless, you can see that these plus and minus states are really good approximations for the actual eigenstates. And that's what we use in the following to investigate the interaction between the quantum dot donor system and the cavity by first transforming the entire Hamiltonian to this plus-minus basis before applying a Schrieffer-Wolff transformation to obtain an effective Hamiltonian for the lower orbital subspace. So by looking at the figure, this means that we derive an effective Hamiltonian for the subspace highlighted in red. So if we have done this Schrieffer-Wolff transformation successfully, we can also account for electron spin mixing due to the magnetic field gradient by introducing electron spin-like basis states that are labeled by the tilde here. And these new basis states are predominantly the respective electron spin state up to small corrections, because the field gradient is much smaller, or is chosen much smaller than the homogeneous magnetic field, and therefore the spin mixing angle is pretty small. Okay, if we also apply the rotating wave approximation, we find these two dominant interaction terms between the quantum dot and a quantum dot donor system and the cavity. The first term gives the flip of both the nuclear spin and the electron spin if the two are anti-aligned, with the concomitant creation or annihilation of a cavity photon. And this term emerges due to the combined effect of the dipole operator and the hyperfine interaction. And in contrary to the second term, it persists in the absence of the magnetic field gradient. The second term describes electron spin flips together with the creation or annihilation of a cavity photon, while the state of the nuclear spin is preserved. And this interaction is the combined effect of the dipole coupling and the magnetic field gradient. Now, these two interaction terms lead to a strong hybridization between the quantum dot donor system and the cavity mode if the respective transition within the quantum dot donor system is close to resonance with the cavity mode. And that's actually exactly what we want to achieve, because the hybrid states lead to a signature in the cavity transmission that can possibly be observed. So this means we have to determine the resonance condition, and therefore it's quite useful to have a look at the energy expectation values of the quantum dot donor system states. To do that, we have to look at the diagonal part of the effective Hamiltonian. And with this, we can find these expectation values for the 4 basis states. And here you see a plot of the energies as a function of the quantum dot donor energy level detuning. Okay, so for a large negative detuning, that corresponds to the case that the electron is confined to the quantum dot on the left. These energy levels here are almost degenerate, and they begin to split as the electron shifts towards the donor. So now we have the energy levels, and with these energy levels, we immediately find the transition frequency for the electron spin nuclear spin flip-flop transition indicated in green, as well as the transition frequencies for electron spin flips with nuclear spin up and nuclear spin down. And what is important to note is that the electron spin flip transition for nuclear spin up is larger than the one for nuclear spin down. And the frequency difference that we denoted by delta is determined by the hyperfine interaction strength and the ratio between the quantum dot donor detuning and the tunnel coupling strength that enters this equation via the orbital angle theta. Okay, so the last term of this Hamiltonian gives the cavity resonance frequency, including small shifts due to the Schrieffer-Wolff transformation. So with this, we have everything together to determine the resonance conditions, and we get 3 of them. 2 for electron spin flips with the nuclear spin either up or down, and 1 for the electron spin nuclear spin flip-flop transition. And as I've mentioned before, we expect that we see a signature in the cavity transmission in the vicinity of parameters that fulfill one of the resonance conditions. So we can try to verify our expectation by calculating the cavity transmission using input-output theory. And here we consider the case that the cavity is probed at its bare cavity resonance frequency. So this means that the probe frequency equals the resonance frequency of the cavity if the cavity is completely empty. Okay, and we present the results as a function of the external magnetic field and the quantum dot donor energy level detuning. In all the plots I'll show, these dashed lines give the points for which the different resonance conditions are fulfilled. So if we now consider the case that we prepare the system in its ground state that corresponds to nuclear spin up, we get this signature here that follows the orange line and therefore verifies our expectation. We can also check the case that the system is prepared in its first excited state with nuclear spin down. And again, our expectation is verified because the signature follows this black line. Finally, the plot here on the left corresponds to the average over many measurements if the system is initialized with equal probability in the states with nuclear spin up and down. So by comparing this plot in the middle and the one on the right, you can see that the hyperfine induced frequency splitting allows for nuclear spin readout. So if you really want to do readout, it's essential to have a strong signal contrast between the signals for nuclear spin up and down. And in order to identify suitable readout points, one can subtract the figure in the middle from the figure on the right. And doing so, we obtain this figure that shows that there are extended regions that provide a high signal contrast for nuclear spin readout in the immediate vicinity of the resonance conditions for nuclear spin up and nuclear spin down. A slightly more detailed analysis is given if you consider line cuts along the lines indicated by these horizontal lines here, and the line cuts are presented in the figure on the right. And this figure unveils that maximal readout contrast is achieved in the immediate vicinity of the resonance condition for nuclear spin up. Moreover, we can check the readout sensitivity with respect to the cavity detuning from the probe field, so denoted by delta omega. And as an example, let's have a look at the signal contrast and the transmission as a function of the cavity probe field detuning for the point where this red and the second vertical orange line intersect. So then we get this plot here on the right, and the solid line that shows the readout contrast shows that a good readout contrast is achieved in a range of several megahertz centered around delta omega 0. But that's not everything that we can learn from this plot, because this plot also shows the origin of the readout contrast. For the selected parameters, so for the parameters selected for this plot, the electron spin flip transition for nuclear spin up is close to resonance with the cavity. And due to the strong electron spin photon coupling, one observes Rabi splitting, as you can see if you follow this dashed line. But on the other hand, the electron spin flip transition for nuclear spin down is off resonant, such that there is no hybridization between the dot donor system and the cavity. And therefore one gets this single isolated resonance that is located in between the two Rabi split peaks. Okay, so with this, I'd like to conclude and highlight the most important points. So we've seen that the hyperfine induced frequency splitting leads to well-separated signatures for nuclear spin up and down. And we expect that these signatures can be resolved individually in recent experimental setups. Moreover, we were able to identify good readout points. Yeah, so if you're interested in more details, I recommend you to have a look at our paper that is already available on arXiv and will soon be published. Yeah, and I'm also open for questions now.
Thank you very much for the nice talk, interesting results, and good timing. Talk is open for questions. At the moment, I don't see any questions in the Zoom or in the Discord, so let me ask my own questions.
Sure.
So I think if you want to do something with this nuclear spin, quantum information processing, you also need to initialize it and also to manipulate it. In this setup, how do you envision those steps?
I mean, so in this setup, there's no way to really control the nuclear spin. I mean, one thing you can do is you can just read it out, and then you know the state of the nuclear spin. So this would be maybe one way to initialize it. I mean, you could also just apply NMR pulses if you know the state of the nuclear spin to change it. And I mean that I think for real control of the nuclear spin, you have to think about other techniques.
Mm-hmm. So would it be a reasonable alternative to your proposal if you anyway have an NMR line? I mean, you have this wire which goes next to your electrons. Then you can do NMR, you can do ESR. So I think the canonical way to read out the nuclear spin in Andrea Morello's experiment, for example, is that they are flipping the nuclear spin information to the electron spin information by an appropriate ESR.
Yeah, they do ESR, right?
So in that situation, you could do like a two-step readout. First, convert the nuclear spin information to electron spin information, and then read that out using that sort of conventional petatarp type of coupling of the electron spin to the cavity. Is that a reasonable alternative?
So I didn't get all the points you mentioned.
So I think the canonical way to read out nuclear spin is to flip the nuclear bit value to the electron spin,
yes.
And then read out the electron spin. And I'm just asking, is that also a reasonable thing to do in your setup? Because my understanding is that in your setup, you can easily read out the electron spin, because that's been demonstrated by.
Yeah, I mean, what we do is essentially reading out the electron spin. So, so in principle, we read out the electron spin, and the readout signal for the electron spin depends on the state of the nuclear spin.
Okay, then let me rephrase the question. So does it worth it to incorporate that micromagnet, the magnetic field gradient? Because apparently you can do the same thing without that, right? If you anyway have an asymmetric line.
Yeah, okay. I mean, if you have this line, it's probably not worth doing readout as we suggested. But if you don't have it, and if you come up with other techniques to control the nuclear spin, I mean, this one would be probably beneficial because you do not need any oscillating magnetic fields. Also for scaling up, probably this would be advantageous because, yeah, I mean, it's pretty hard to confine oscillating magnetic fields to a specific position in space.
Related question. I presume that also in silicon you have some spin-orbit interaction. Would that be sufficient? I mean, could that replace the magnetic field gradient?
I mean, it probably depends on the strength of the spin-orbit interaction. So
based on the knowledge from the literature. So Menno, for example, did measurements on how strong spin-orbit interaction is in quantum dots.
Okay, so I don't have the numbers in my head, so I'm not sure what spin-orbit interaction strength would be sufficient for the readout technique.
Okay. Good. Thank you very much for the talk and also for answering the questions.